We're going to see now some problems on one dimension, kinematics in one dimension, which is motion in a single dimension, therefore is motion in a single line. Now when we have motion in a single line, we're going to have position, velocity, and time, and acceleration, but everything is going to happen on a line, so we're only going to need one coordinate to describe each one of those components of the motion. Now because we are only studying motion with constant acceleration, uniformly accelerated motion, we will never need to have two accelerations, an initial and a final acceleration. We only have a given acceleration which is constant throughout all the motion. Now when we think about it, in reality we have 6 parameters with which we can play. We're going to have the position at a given time and the initial position. We're going to have the velocity at a given time and the initial velocity. We're going to have the acceleration which is constant and the time taken. This is of course assuming 0 initial time and 0 initial time and constant acceleration. Now the entire goal of any problem in kinematics is the problem gives you 4 of these as a given. It is asking for a fifth one, which is the question of the problem. So let's say 4 are given. 1 is asked, and 1 is missing. It's important in every problem in kinematics that we start by writing first and foremost all the information that the problem gives us, which are the 4 of these variables that are given in the statement. Then we're going to identify which is the one that's being asked, and then therefore we know which one is the one that is missing in the information. Now we can go to the equations that we have figured out on derived in lectures. So we have equations, which are 5 equations over here that describe every single possible scenario. What distinguishes them is what's missing. So when you're missing the velocity at the given time, then you use the classical kinematic equation for one-dimensional motion. When you're missing information about the position, whether it is the initial or the final or the position at the given time, in any ways the displacement, you're going to be using this equation. When you're missing the time, then you can use this equation. All 3 equations we derived in class. Now there's 2 extra equations that are rarely used but might be worth adding. What happens when you don't know the initial velocity? You actually can derive this based on this and this one from what we saw on the lectures. What happens when you're missing the initial velocity? Then you have the position, the initial position, you have the velocity at a given time, the time it takes, and the acceleration. You can use this equation and then solve for whatever one of the parameters you need. And finally, there are instances where you're missing the acceleration, but you can use it. You can figure it out when you know velocity, you know initial velocity, you know time, and you know position. Now it's important to notice, every time that you have a problem and you're one missing, the missing one is going to give you which of the equations you use. However, it doesn't mean that you're always solving for x. It might be that you are missing the velocity, but they're asking you about the initial position. In this case, because you're missing the velocity, you're going to use this equation, but the one that you're going to have to solve for is the initial position, not the final position or the position at a given time. So then this is an important note to have in mind. These equations decide which equation to use based on the information that is missing, not based on the information that's being asked for. We then solve this equation for the variable that we are being asked for. So let's see a few examples on how to use this. Now let's read together this problem and identify the information that is given, what is missing, and what is being asked. It says there's an object that starts from rest with a constant acceleration of 8 meters per second, square second. Now I can write all my parameters in here. So position, initial position, velocity, initial velocity, acceleration, and time. And the first thing they're telling me is that there is an object that starts from rest. That starts from rest means that there is 0 initial velocity because it starts from rest. Then it has a constant acceleration of 8 meters per square second. And it moves along a straight line. Of course, it moves along a straight line. It means that it is one-dimensional motion, and it is with constant acceleration. Therefore, we can use our set of equations. And then it's asking us what is the speed at the end of 5 seconds. So we're being questioned about velocity after 5 seconds. Now, what is missing here? This is what we're trying to find. But the position and initial position are missing. In other words, we're missing the displacement. So we can go to our equation, find which one we're missing, which is displacement, Identify the equation and write it down. Velocity is equal to initial velocity plus a times t. And now the question, of course, is let's solve for velocity, which in this case is very convenient because it's the first parameter. So we just go to our set of data and replace. So the initial velocity is 0, acceleration is 8, times is 5, so then this is 40 meters per second. As simple as that. So we want to know what is the velocity 5 seconds into the motion for an object that starts at rest, moves in a straight line, and has this acceleration. Simple. We identify we didn't have any information on the position, and in fact we don't. It's implicit. So then we can use this equation and find out 40 meters per second. Now the problem asks next, what is the average velocity? And again, we have an equation that we know from the language of motion, the previous chapter, when we know the average velocity calculated by, or the formula given by Merton, the Merton mean speed theorem was given by the sum of initial and final velocity divided by 2. Now, what's the final velocity at 5 seconds? We do not know, but we just find out, right? So then we can use the result from part A into part B. So we're going to plug 40 meters per second. We're going to add the initial velocity that, of course, is 0 because it started at rest. We're going to divide, and we're going to find 20 meters per second. Does this make sense? It's a good idea to, every time that you solve a problem, figure out, does this number make sense? Now, if the motion is starting from rest and is reaching 40 meters per second, of course our average cannot be larger than the maximum velocity, which is 40 meters per second. This object is always accelerating. We never were told that it decelerates or brakes or anything like that. Therefore, it's never going to be larger than this. And actually it kind of makes sense because it's halfway through 0 and 40, which is exactly what we're doing with the formula. Now in the last step, we're going to be asked about what is the total displacement or the displacement of this motion after 5 seconds. So this is the one that the only piece that we're missing because we have figured out now the velocity. Now we can come up backward equations, and then we need to find a scenario where we are finding for these two ones, actually x minus x0, which is this one over there. We have also x and x minus 0 here, so we could use this equation. We could also use this equation, but this has a square, so it seems to be a little bit inconvenient because we're going to have to square velocity and this velocity and then divide by 2 times a to solve for delta x. There's a simpler equation in this case, which is this one over here. This one directly tells us that the displacement is given as the final velocity plus initial velocity divided by 2, in other words, the average velocity times the time. And so if we replace the numbers, the final velocity we just calculated in part A, that's 40 meters per second. The initial velocity is 0. We got it from the problem wording, and we divide by 2, and then we multiply times 5 because it's 5 seconds. Now we can just 40 divided by 2 is 20. 20 times 5 is 100. So we have 100 meters. So how much has this track or this object moved? In 5 seconds, it has moved 100 meters. And with this, we complete the entire description. We were given initial velocity, acceleration, and time. We were asked first for velocity. Position was missing. By the end of this exercise, we have been able to figure out everything. Again, you identify the information that you have. You identify the information that's being asked. You identify the information that is missing. You go to your equations, find the one that's missing, use the equation and solve it. At some point, you have all the information. In fact, you don't have 4 but 5. At that point, you have more than one option to use either one of these equations to solve for the 6th piece of information that is missing in the problem. Let's see another problem in one dimension. In this case, we have a track which speed is increasing uniformly from 15 kilometers per hour to 60 kilometers per hour in 20 seconds. Now it's important, the first line says track speed increases uniformly. Is telling us the acceleration is constant, therefore we can use our set of equations for motion in one dimension with constant acceleration. Now let's identify every piece of information that the problem gives us. Let's write our matrix here, and let's figure it out. Okay, so the first thing that the problem says is that it goes uniformly from 15 kilometers per hour, therefore 15 is the initial velocity. It increases to 60 kilometers per hour, so we can write 60. And it takes 20 seconds, so we have time. Now the first question in the problem is what is the average velocity? The average velocity, as we remember, is given by final velocity plus initial velocity divided by 2. And so the first question that we ask ourselves is, do we want to work in kilometers per hour, or do we want first to convert kilometers per hour in meters per second, which is international system units, and so solve the problem that way? I think it's more convenient to always first convert every single unit that you're giving into international system, because then you avoid troubles down the line. But this is completely up to you. You could work provided that both are in the same unit system. You could add them together and then the result converted into meters per second. In this case, we're going to do that, but you can do it the other way. Probably practice that and make sure that you obtain the same result. So in this case, we have initial velocity 60 kilometers per hour, final velocity is 15 kilometers per hour, and this is divided by 2. So this is 75 divided by 2, which is 37.5 kilometers per hour. Let's make sure that 37.5. Okay, so 37.5 kilometers per hour, then we have the average velocity, let's write it down, 37.5 kilometers per hour, and we want to convert it into meters per second. So how do we do so? Well, we need to convert both. 37.5 is the number, remains the same. We know that 1 kilometer is 1,000 meters, and we know that 1 hour is 3,600 seconds. Now we can make that division and multiplication, and we're going to find that this is about 10.4 meters per second. So that's the average velocity, the first thing that they ask in the problem. Now the second part of the problem says what is the acceleration of this object. Now we have velocity, we have time, we're being asked about acceleration, right? We are missing position. So we go to our equations and we say, what do we do when we are missing acceleration? When we're missing position, we have velocities and we want to find acceleration. Then we get the equation and then we write down v plus v sub 0 plus a times t. And we want to solve for acceleration, therefore we're going to have to go first. V sub 0 goes there, and then we have at, and then finally t goes dividing, therefore we're going to find v minus v sub 0 divided by t is equal to the acceleration. Now we want to find the acceleration, then we just need to replace the numbers. Again, this is v minus v sub 0 divided by t. V is the final velocity, we know it's 60 kilometers per hour. And again, we should have converted these numbers. So let's do some magic in here. So then we find velocity in meters per second, finally 16.7, so that 16.7 corresponds to 60 kilometers per hour, 4.17 corresponds to 15 kilometers per hour. We actually can round up this to be 4.2, need to be that detail. And so we can come back here and then use international system. This is why one of those scenarios where we see why it was more convenient to first convert the units and then use those international units for the rest of the problem. But basically we're going to have to subtract 16.7 to 4.2, which is the initial velocity, and divide that by the time taken, which is 20. Now 16.7 minus 4.2 is 12.5, and 12.5 divided by 20 is going to be 0.625. And that's going to be meters per square second. Why? Because we have meters per second divided by second, so we have meters per square second, which are the units of acceleration. So we find out then what is our acceleration, 0.625 meters per second square. That means that every second this track is gaining 0.625 meters per second. So the first second at the beginning is 15 kilometers per hour, which is 4.2 meters per second. The first second of the motion is going to be 4.2 plus this. The second is going to be 4.2 plus this plus this. The third 4.2 plus this plus this plus this, and so forth. Every time, every second, we gain the amount of acceleration given, and that acceleration is constant, so it happens all the time. Let's find out the missing piece of information in this problem. Finally, the problem is asking us to find what is the distance traveled. So we're trying to find delta x. Again, another example, we're missing acceleration, we found it out, and then we're missing this one, but we have everything else. So in reality, it's not that we're missing, it's actually we're trying to find out. So if we're trying to find out what's the position, but we have everything else, again, we have total freedom to use whichever equation we want, which in this particular case is very convenient to use this last equation because we have delta x already here, but we could also use this equation. So just to make a change, let's use this equation instead. So to find, and then you can try yourself to use this one, which is much faster, but just to see that actually it works the same way. So to find that, we're going to use that the square velocity is equal to square initial velocity plus 2 times acceleration delta x. This is what we're trying to solve for, so this is going to have to come back here subtracting, and then we're going to have plus 2a delta x. Now this is going to come here dividing, and so finally delta x is just going to be v squared minus v squared 0 divided by 2 times the acceleration. Now of course you see why this is much less convenient to directly plug velocity, add them together, divide by 2, multiply times 20. But both give exactly the same result. So if we replace numbers in here, we're going to find that the displacement is equal to v squared. Now v is 16, so it's going to be 16.7 squared plus 4.2 squared, minus, is a square we are subtracting, divided by 2 times the acceleration, and the acceleration is this, so 2 times that is going to be 12.5, so it's going to be 1.25 meters per square second, and so by plugging these numbers into the calculator we can find the answer. So that's going to be 209 meters, which you can convert into whichever unit you want. In the case of kilometers, will be 0.2 kilometers. But that's the total displacement in that motion. So we've gone again with another example where we identify the information that we have, we see what's being asked and what's missing, and from the missing we pick up our equation. Once that step is solved, then we have 4 of our incognitas or 5 of our incognitas, then we have total freedom to choose the one that is more convenient to us. In this case we chose this one, which is inconvenient. It would have been much faster to use this equation, because then you would have 16.7 plus 4.2, that's 20.9, divided by 2 is 10.45, and then times 20, you're going to find 209 meters. So that would have been much more faster, but again, you have total freedom. This idea of which equation to use at this last step is going to be up to you, and it is a matter of practice to get the idea of which equation, and actually just taking a look which equation is more convenient for the particular problem that you have at hand. Let's do one last problem on one-dimensional with constant acceleration. This is a free fall. In free fall we have constant acceleration because acceleration is accelerational gravity, which is g, which is 10 meters per square second, 9.8. That's pretty independent of, as we will see, of the mass of the object itself. It's just purely a number given by the distance to the center of the Earth, which is the one making the pulling, so to speak, and therefore accelerating, as again we will see in dynamics chapter. The question says there is a ball dropped from a rest at a height of 50 meters above the ground. What is its speed? The first question is what's the speed just before it hits the ground. Now let's write again our equations. Now, because this is a free fall, so we can imagine someone maybe at the top of a building letting an object fall. Right, the object is being accelerated obviously with g, which is 10 meters per square second. Because we have vertical motion, we could use y instead of x. You can use x, it doesn't matter, you can use whatever you like, just make sure you understand your own notation. So, the question says that the object is dropped So the object is dropped from rest, and here we have to stop and realize if it's dropped from rest, they're telling us that the initial velocity is 0. It's dropped from rest. From a height of 50 meters, what's the initial height? 50 meters. From the ground, and we want to know what is the speed just before it hits the ground. So we want to know what's the velocity at the ground. Now it might seem like we only have 2 pieces of information. This looks very difficult, but in reality we have more. Because this is an object that is dropped, we know that the acceleration is actually minus 10 meters per square second. You could use 9.8, I think it's just very bothersome, so let's use 10 round up. We're interested in the concept, not in the exact number in this sort of problems. So we can use negative 10. Why negative? Because it's going downwards. So now we have an extra piece of information. Do we know the time? We don't really know how long it will take. Do we know the velocity? Well, that's actually what's being asked. Do we know the final position? And the truth is that you know the final position because it's actually given in the question. It says what is the speed just before it hits the ground. Now the ground is here, so what would be an instant, an infinitesimal time before it hits the ground? Because of course after it hits the ground, let's say the motion ends, so the velocity will be 0. But important, the velocity of an object when it reaches the ground is never 0 in free fall. That's the reason why you never stand down a window when someone is throwing something, because if it hits you with 0 velocity, it will be no problem. 0 velocity is a table standing on the room, right? The table is not moving, velocity is 0. But an object free falling, just before it hits the ground, just an infinitesimal, so to speak, an instant before it hits the ground was the velocity, then we know that the final position is actually 0, because we want to know when the object hits the ground. And so we can find now the velocity. We have a scenario where we have initial and final position, we have velocity, initial velocity, we have the acceleration, and we're missing the time. Because we're missing the time, we go to our equations, we see the one we're missing, we know what equation to use. So v squared, it's equal to the initial velocity, which is 0 squared, plus 2 times acceleration, which is 10, times the difference in position, and that's going to be 0 is the final position, and 50 is the initial position. So very important here to bear this in mind. So we're going to have 2 times minus 10, 0 minus 50 is minus 50. This is minus 50 times minus 10 is 500 positive, negative, negative, positive, times 2, that's going to be 1000. So we find that the final velocity is 1000, but this is final velocity squared. Therefore, velocity is going to be the square root of 1000. Square root is which number multiplied by itself gives you 1000, and that of course it's going to be about 31.3 meters per second. So now we have the velocity when it reaches the ground, which is 31.3 meters per second. So 31.3 meters per second. There's one point to bear in mind in here. Velocity is positive and we were falling down, so we wouldn't expect a positive velocity. That is because the velocity was a square, and if you remember, every time that you have a square root, you can have a plus and a minus when solving an equation in front of your square root. Now, because you know the physics of the problem, then you have to make sure that you enforce that, and in your solution you pick up the negative root, because negative 31.3 squared is indeed about 1000, and therefore this is the right solution. The object needs to be falling down, so it needs to have a negative velocity. So we need to say that the velocity is smaller than 0. If velocity was positive, we would be claiming that the object is going upwards. So this is an important thing to bear in mind. Sometimes the math, you need to be careful to pick up the right solution. So we find finally the velocity. Velocity is negative 31.3. Again, this is one of those cases where you make a sanity check at the end of your math and make sure, oh, if it's positive, check out where's the problem. Oh, the problem is here, that the square root actually could be the positive or negative. We're solving the equation. There needs to be 2 solutions. Solutions are plus 31.3 and minus 31.3. The one that we need to pick up, because the one that we need to pick because it is what makes physical sense, is the negative 31.3 meters per second. So important thing, bear in mind that. Now part B asks how long will it take to make this. Again, as an example, we were having this information, we were missing this, we found it out, now we have the final position, final velocity, initial velocity, acceleration, and the one missing can be figured out. Now we could use any equation that we like, but the one that is more simple to solve is actually this one over here, because acceleration is here, we know velocity, and we can solve for t. You could use this one, you could use actually this one because it also has time, and you could use this one because it has time, but the easiest one probably to solve for now is this over here. So let's just say, what's the time? The time v is equal to v sub 0 plus a times t. Therefore, v minus v sub 0 is a times t. Therefore, times is just equal to v minus v sub 0 divided by the acceleration. If we replace with the numbers, final velocity is minus 31.3. Initial velocity is 0, starts from rest, divided by the acceleration, which is minus 10. Important the sign. This and this minus are going to cancel, and what you're going to find is that the time it takes is 3.13 seconds to fall. Now, this is a free fall motion. The motion, it takes 3.1 seconds to fall 50 meters. This is universal for any object, disregarding, of course, the effects of air friction. Any object is going to fall on surface of Earth in about 3.1 seconds, 50 meters. This is always the case. It's relevant, regardless of the object in particular that we're considering. Important thing, if by the end you reach time you have a negative number, you've done something wrong. So go back and check where the sign went wrong. In this case, because we have negative, 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 that's going to be negative anyways, divided by negative, that's going to be positive. If we had solved the previous result without realizing that this was negative, we left the positive, then we will have a positive divided by negative, that would have been negative. So again, that would have been a good point to realize, oh, we did an error somewhere. Go back and check out where's your error. In this case, we realize velocity is negative, therefore time ends up being positive. You cannot go back in time, so time is positive. Okay, so let's solve now problem 8. Problem 8 is about vertical motion. And the first thing probably to notice is that we have changed the equations. Now they're the same one-dimensional questions, but now they're going to be in vertical motion. So we are using subscript 2y and position y and y sub naught, or y sub 0, also b sub 0 y. And we have also replaced acceleration with g, because in every vertical motion, there's vertical motion because there's gravity, and gravity produces a gravitational acceleration, which is g. On Earth, g is minus 9.8 meters per square second. It always points down. It always points to the ground, right? So if this is the Earth and you have an object here, the object gets a gravity towards the center of the planet. So this is going to be, let's say, g. So it's going to be in the negative usually if you decide your axis to be negative. If the planet is not Earth, then gravitational acceleration is going to be something different. For instance, for the moon is, I think, 1.6, and in fact, this problem addresses a situation on the moon. It says there is a ball that is thrown straight upward on the moon with an initial speed of 35 meters per second. So the way to solve this is going to be exactly the same thing. So we're going to write here the information that we have, and we're going to identify the things that we don't have, right? So y sub naught, where is this? So it's going to be y sub naught equals to v and then times t. So these are going to be the equations. So the first thing it says is a ball is thrown straight upward on the moon with an initial speed of 35 meters per second. Now it's thrown upward, so the velocity is going to be plus, and it is 35 meters per second, so we just write 35 meters per second. Sometimes it might be useful just to make a small cartoon of the situation. So let's say you're just here and you're just throwing a ball upwards and then you're on the moon, right? So then you can define that this is the positive direction, and so everything down, pointing down, is going to be negative, and if you go down, it's going to be decreasing the position. So we first identify 35 meters per second, and then we say due to the gravity there is 1.6 meters per square second. Now it's 1.6, but now instead of being 10 as on Earth, but it's going to be also negative. Why? It's going to be meters per square second, so let's just put it here, because it's pointing down. So objects on the moon also fall, but they fall about a tenth, a ninth, or an eighth actually of the gravitational acceleration of Earth. And so we have this information, and then it says it's thrown upwards, and compute first what's the maximum height reached by the ball. Now this is a very classical question asked in vertical motion, which is the maximum height. The maximum height is always going to be determined by the initial velocity, and that is why, obviously, if you drop an object, the maximum height is wherever you drop it. But when you throw the object upwards, you're going to have certain velocity that's going to be cancelled, or is going to be reduced by the gravitational acceleration, and that's why the object reduces velocity, it stops, and then it starts going downwards. So from the question, what is the maximum height, what we can of course infer is that we're asking the position when the velocity, the vertical velocity, is 0. The maximum point, excuse me, the height of maximum, the point of maximum height is going to be with velocity 0. So now we know that we have velocity, we have gravitational acceleration, we have the initial velocity, and now we are missing both time and information about the height. Because they don't say anything about that, we can always assume this is 0, but just let's just write 0. And what about the time? We don't know anything. So the thing that we're missing is actually time. So we go to our set of equations and we figure out which is the equation that addresses a problem when we don't have any information on time. This is this one over here, so we just can write it down. So it's going to be the square of the velocity. It's equal to square of initial velocity plus, and then we're going to see it's 2 times g delta y, right? 2 times g delta y. This is actually what we're trying to find. If we remember that delta y is just simply y minus y sub 0. So if we take this to be 0, that's going to be the maximum height, just directly. But the other thing we need to notice is when we replace the numbers, v squared is going to be what? Final velocity. This is a maximum height. So that's going to be 0. It's equal to initial velocity squared, which is 35 meters per second. So that's going to be 35 squared plus. And now we have a plus 2 and g, but g is going to be negative. So don't forget the sign of minus 1.6 and then times delta y. Now, of course, we can just solve for that. That's going to be delta y. It's just simply, this is adding up, so it's negative, so it's going to be minus 35 squared, right? And then this is multiplying, so it's going to come dividing, so it's going to be 2 times minus 1.6. And if you make the math, the result that you obtain is 380 meters. So the maximum height that you achieve with an object that is thrown upwards on the moon at 35 meters per second is going to be 380 meters. Now it's an interesting thing to notice here. There is no mass anywhere in here. That means any object thrown on the moon with this velocity will always reach a maximum height of 380 meters. It doesn't matter if you throw a piano or if you throw a feather or a pencil or whatever you throw, because again, there is no room for mass in here. A different question that we will study in chapter 2 is going to be how much more difficult it's actually to throw a piano or any other object for that matter, because then we need to accelerate the object, or in this case to produce that velocity, and that's going to be more challenging, of course, with a piano than with a feather. But the fact that both objects, if they're both thrown with this velocity, both will reach the same height. Now the second question is asking us how long does it take to actually reach that maximum velocity. So if we're actually doing maximum at the maximum point, that's going to be of course 0. So we obtain the maximum height. Now we know the maximum height, we know the initial final velocity because it's given, it's just the point of maximum height, what's the gravitational acceleration and what's the initial velocity. Now the missing parameter that decided which equation we were going to be used now is the one that we're being asked. But now of course we cannot use this equation because there's no information to get any more from here. We need to use one of the other ones. And in fact we have to use, or we can use the one that's more convenient to us. So I think the most convenient now is going to be to use this equation over here because we can just solve for time. It will solve. If you use this one or this one, then you're going to have a quadratic equation to solve. You solve for t with 2 values, positive and negative. We'll see for parabolic shot that when you have the square root to solve, you're going to have 2 solutions. An object going up and then going down is always going to have 2 solutions for a specific position except the maximum, because the object goes up and then it goes down. So this point is the same height as this point. Both objects are going to have the same height at 2 different instants of time. So this is going to be t and this is going to be t1 and this is going to be t2. So when you're solving for time for a given height, you're always going to have 2 solutions. Now, solving for time, we can just write the equation, any of the equations. If we want, we can just directly use this one. So if we use that one, we're going to find that the final velocity, of course, is, we can use this equation. Why? Because now we know the final velocity, which is 0. We know the initial velocity, which is 35 meters per second. We know the gravitational acceleration, which is 1.6 negative, and we want to find the time. So again, we just can solve time. So this goes here, and then the 1.6 goes dividing, but because this was negative, passes as positive, and then divides as positive. And if we do this, we can find out how long does it take to actually reach those 380 meters per second, and the solution is about 22 seconds. So it would take an object, any object on the moon thrown upwards with 35 meters per second, 300, it will reach a maximum height of 380 meters in 22 seconds. So imagine you throw something up and it takes 22 seconds to reach there. Obviously on Earth, because gravity is higher, it will be much less time and it will be also much less distance. Now the next question is asking us, what is the velocity at time t equal 30 seconds? Of course, because we know the maximum height is going to be achieved at 22 seconds, the object is going to go up in 22 seconds and then it's going to fall 8 seconds. We're asking for that height, and obviously we immediately know that height is going to be less than 380 meters. If we obtain a solution that is more than 380 meters, we know we got a wrong solution. It's a sanity check. And also because the motions in vertical motion, the acceleration is constant. When I throw an object with velocity upwards, the velocity is going to be reduced all the way up to 0, and then it's going to be inverted. So by the time the object reaches down, where I have thrown the object, the velocity should be the same as the initial, but negative. And so we also have in here an idea, which is that every vertical or every free fall, as this is an example of free fall, it's always symmetric. And obviously this applies when we're in a level surface. If we have certain height, for instance, we throw in out of a building, then we have to assume it's symmetric with respect to the roof of the building, right? The object is going to be thrown with a certain velocity is going to reduce to 0 and increase again. And the rate of increase is actually the same as the rate of decrease, and it takes the same amount of time and the same distance to go up to go down. Therefore, the velocity is going to be always positive and exactly the same but negative when the object is coming down. So we can write down the equations. Now we're not having any more the velocity is 0. That was for the previous case. Now that's actually the question we're asking. We have no information about the position. We have information about initial velocity. We have information about time. We have information about gravitation, because we're being asked this, and we don't have in this case information about the space. We find the equation that applies, which is of course this one, and then we just write it down. So that's going to be Vy is V naught y plus gt. We replace with the numbers, and Vy it's going to be equal to the V naught, which is 35 initial velocity, plus minus 1.6 and times 30. Now this is about 48, and 35 minus 48, excuse me, that's 30, obviously, 30 seconds. So that's going to be minus 13 meters per second. So what's going on? We can make a small cartoon here. We throw the ball with 35 meters per second. The object is going to reach a maximum height, let's say, of 380 meters. A maximum height of 380 meters. Then it's going to fall down, and at some point here, it's going to have minus 30 meters per second. And again, this is the idea we were just discussing. 35 meters per second positive is going to go all the way down to 0, and then it's going to start decreasing the velocity until at 30 seconds, which is 8 seconds down the 22 seconds that it takes to reach the maximum, the object is going to have minus 30 meters per second. If we calculate how much time it takes to fall, then we can use the same equation and figure out what's the velocity at the when it fell. When it touched the surface, it's going to be, again, negative 35 meters per second. It's always the same case. It's always symmetric.